In this problem set, we are going to solve two problems. In the first case, we are going to get the natural frequency of this system. And in the second part, for the same system, we will try to find the response for the free vibration case. This picture is just same as we have seen in this case, but it is just rotated by 90 degree. So let's try to find the natural frequency of this system. If you will see the system, there are two springs connected, K1 and K3. Magnitudes are given here. Mass is 3 kg and a member is connected between the two springs. One end of the member is fixed. That means we can consider this massless member as a beam, as a cantilever beam. And once we are having a cantilever beam, we can include the stiffness of this cantilever beam. First, we need to find the stiffness of this cantilever beam, which is massless, and we have already seen previously that the stiffness of a cantilever beam is 3EI by L cube, where E is the elastic constant, I is the second moment of area, and L is the length of the beam. Second important point, how the springs are connected. We must understand that if we are having a cantilever beam and then we are having a spring attached here, this is K1 and K2. If I will try to pull the point in the downward direction, both these springs will try to resist the motion, and displacement in both these springs will be same. So we can just recall the philosophy that if the two springs are connected in the parallel, both will have equal displacement. Here we can understand that this K1 and K2 are actually connected in parallel, and the system then further connected in series with K3. So the equivalent system of the given will be K1 and K2, and then we are having K3. So I can further simplified my system by considering only two springs. So this will become K1 plus K2, and this will be just K3, and my total stiffness will be 1 by K1 plus 1 by this summation, K3 in this summation. So first calculate the stiffness of this beam. So when I will put all the value together, I will find that the natural frequency is what? 1200 Newton per meter. So here this 1200 and this 1200 are in parallel. So 1200 and 1200 will become 2400. So my final system will become like a 2400 Newton per meter spring connected with again a 2400 Newton meter spring in series, and there is a mass. So my net spring stiffness will be just half. I'm just quickly running through it. If you are having a problem in series and parallel connection of the spring, you can watch other videos. So finally I will get a spring constant which will having the value of 1200 Newton meter, because 1 by 2400 plus 1 by 2400 is equal to 1 by K total is going to give me the K total is equal to 1200 Newton meter. After finding the final stiffness, we can calculate the natural frequency, that is nothing but under root K by M. K is the total K, and it is just 1200 by 3 under root. So I will get under root 400, that is 20 radians per second. Please remember, this is the natural frequency but in radians per second. After finding the natural frequency, our next job is to find the response of the same system. So this is the same system where this was K2, K1 and K3. Here is the mass. I am exciting the mass using this pendulum. It is given that the collision is pure elastic. The mass of the bob of the pendulum is 3 and the mass is again the 3. So we can recall that if we are having two equal masses, one is stationary and another one is moving, then there will be complete exchange of velocity. That means when the pendulum will hit the mass, whatever velocity pendulum will be completely transferred to the mass of 3 kg. So I need to calculate the initial velocity of this mass 3 kg by using the final velocity of the pendulum, and in case of a pendulum, equal the potential energy and the kinetic energy of my pendulum. So it will be mgh and half mv square. So the velocity will be under root 2gh. When I will put all the value, that 2 in into 0.2, I will get it is 2 meter per second. So the input for the given mass is 2 meter per second, and if you will recall, This is a single degree of freedom system, and if we are having a standard single degree of freedom system, the input condition will be x naught and x naught dot. This is initial displacement and this is initial velocity, and we know that the response of the system is just a cos omega nt plus b sine omega nt. We can further simplify. If the given condition are x naught and x naught dot, displacement and the velocity, I can write that x naught cos omega nt plus x naught dot by omega n sine omega nt. If you still having confusion in this statement, you can go and watch my previous video where we have studied the single degree of freedom system and the response of the single degree of freedom system. Here we are just solving the problem. So this would be my final response, and here we know that the x naught is 0 because the pendulum is just striking, and whenever we are having a collision kind of thing, the input condition is just velocity, there will not be any displacement. That means x naught is 0 here, so my response will be what? 2 by the natural frequency, and the natural frequency is, again we have calculated here that the natural frequency is 20 radians per second, so it will be 2 by 20 cos 20t. This is the response. I can put any value of time and I can get the position of my mass. If I am interested to find the velocity at any given instant of time, what I need to do, I have to further differentiate the same statement, and even I can get the acceleration. So x dot t will give me the velocity, that will be 2 by 20 into minus 20 sine 20t. And if I will further differentiate it, I will again get the acceleration. At this moment, I would also like to add, suppose we are having the same problem, but in addition to this collision of the pendulum, a displacement input is also given. If assume that the mass is also having a pull in this direction, and that is of, let's 4 centimeter. So here, if I am going to consider the mass, you can visualize that initial velocity is in this direction, but initial displacement is in this direction. So when you are going to put this equation, you have to consider one positive, then other one will be negative, and that sign can be exchanged. If you are considering that the left direction is the positive, the right direction will be negative, or if the displacement is the positive, your velocity will be negative, and you have to put both the values. So here, if I will have a 4 centimeter input as well as I am having a 2 meter per second input, my equation will have that minus 0.02 cos omega nt, because this is the displacement, and then I will put plus whatever value I am having in this expression. So I hope that with this quick explanation, now you are able to understand how you can find the natural frequency of this sort of system, as well as you can also calculate the response. Thank you.